The first speaker of this semester in the famous experimental math seminar of Rutgers University is my co-organizer, Stoyan Dimitrov, who will speak about picking, posing, and attacking natural problems in discrete mathematics, from insightful bijections to black box help from machine learning. As usual, please mute yourself unless you have something to say. Go ahead.
Thanks, Dr. Zia. I'm happy to be back to speak at my favorite seminar I attend since COVID time. So the plan was that this is like a job talk training. Hopefully, I will get some interview this year. So I should admit I haven't trained much, but the content is all here. So I just thought a bit what could be a very general topic related to my research, but also appropriate to hear from diverse set of researchers that usually attend job talks. And because of that, I decided to start with this very general question. I would say $1 million question. What should be the goal of the math researcher? And of course, speaking of the purposes, our goals and purposes when we're doing math, we have the famous dichotomy of mathematicians to problem solvers and theory builders. However, a little less famous names, lesser known names for the same dichotomy are namely frogs and birds. So these are another fun names coined by Freeman Dyson. Here he has a famous essay, Birds and Frogs. And indeed, instead of problem solvers, he says frogs. Instead of theory builders, he says birds. And okay, the idea is that frogs see only in the flowers that grow near them. So they are more interested in specific problems. So there is this analogy here. Whereas birds or theory builders are, they fly high in the air and divide in concepts that unify different work from different areas. So in terms of this dichotomy, I should say I'm close to a prototypical frog as a combinatorialist, and I believe naturally for all of us discrete mathematics, we are more like frogs. We are oriented towards problem solving and specific problems first. But okay, since I'm more of a problem solver, I decided to discuss with one slide this general importance of picking good problems. Right, and I here selected a few quotes which I like about this question, very high-level question. So the first one is by Giancarlo Rota, who said that mathematical research is not about solving problems, it's about finding the right problems. And also another kind of peculiar quote from Vladimir Arnault is saying that to select a problem for your PhD student, that's the same as to choose a bride for one's son. I kind of like this quote because, okay, when I try to work with students, I also saw that it's way better if you show them a bunch of problems and they pick one themselves to work on. The motivation is much better, higher. And finally, I selected another quote from the famous Vladimir Vapnik, who lives here in New Jersey, as far as I know. And he says, from the perspective of a machine learning researcher, that how people ask questions is the most difficult thing to understand in order to mirror intelligence and to construct this AGI, this very powerful machine learning agent. And okay, here a small remark that probably Dr. Z would like is that nowadays, when we have computers, actually picking a good problem is even more important because we can dig more with computers more easily.
Yeah.
Some comment? No? Okay. Okay, so picking good problems is certainly very important, but what is actually a good problem? A few words about that as well. So in the first place, the problem should be very natural, which when we say this word, we typically mean to have succinct formulation, right? Some concise formulation. But okay, what is the reason that we prefer such problems? So first of all, that they're nice to share, they're easy to share with other mathematicians, but also if the problem is natural, it has higher chance to pop up in other settings. That's another very important reason. So for example, one thing that I like to emphasize during my classes is that all these famous objects like Fibonacci numbers, Catalan numbers, the numbers pi, e, even the normal distribution, these are not some miraculous objects, but they just satisfy some very simple properties. And that's why they pop up frequently in multiple places, and we see them very often. Okay, good. So the problem should be natural, but also another characteristic is to have some motivation, because we could ask very many neat problems, but we also prefer to have some motivation coming maybe from another branch, say computer science or physics. Good. Also, I would add that if the problem or the conjecture we try to prove is sort of surprising, that's also a plus, because it speaks that probably it indicates that probably there is a lot related to this problem that we don't understand, and we can find a lot of valuable new knowledge. And finally, there is this trade-off whenever you pick problems. The problem should still be unsolved, but also not super difficult, so that you can actually attack it. And yeah, of course, we should be excited and curious about the answer of the problem we pick, because research is hard and it takes lots of effort and months, sometimes years. Okay, some sources of good problems for me. I very quickly tried to mention here: workshops, reading group, seminars. Also, I found for myself that following my research heroes or some people that I admire for their research work is very helpful, because this gives you more motivation, and your interest is naturally more if you follow the work of people you like instead of reading random papers online. But of course, certainly from time to time, reading the new archive papers also helps. And here I would also like to say that sometimes looking at some textbooks on fundamental knowledge is another unusual source of ideas and problems, because natural problems are very much related to, often related to some fundamental knowledge, undergraduate knowledge. And okay, good. So we have some sources of problems and ideas, and we have two options: either to see an existing problem and to pick it, to work on it, or to pose our own problem. And here I would like to say that for me, problem posing is underrated these days, and decided to add this funny quote from Jim Simons, who said that I'm not such a fast runner if I'm one out of n people all working on the same problem. Maybe won't be that fast, and I have little chance. So instead, yeah, he's saying if he formulates his own problem that he likes, maybe he has a better chance. And here speaking of that, I would like to illustrate, to talk about a few specific, very general ideas, how one can pose new problems. And for the examples, I would use some problems actually posed by Herbert Wilf. And okay, the general settings are, if we have a set of objects, say the set of partitions, then how can we come up with new problems about this set? And of course, Herbert Wilf was a great problem poser, so that's a good person to look for examples. So, okay, the first general idea is, okay, if you have such a set of objects, maybe you can take part of these objects and ask a question about this part. So for instance, here, for the partitions, he asked, okay, if we take every even indexed parts, the partition that is formed, okay, if that sum is equal to m, then how many of these partitions do we have for fixed n and m? Also, okay, another general idea is, okay, maybe we can take a collection of these objects and ask a question about the collection. So here is another example of this sort. Again, a question asked by Wilf. Two more such general ideas are to ask a probabilistic question, maybe take a random object in our set and ask a reasonable question about it. And finally, maybe having my set of objects, I can perhaps define a graph somehow over this set and ask a question about this graph. Okay, so that's one example, another question asked by Wilf. And okay, so that was like the introductory entertaining part of the talk. So now, after I discussed what is a good problem for me and how some ideas about asking new questions and posing new questions, I would like to tell you about some of my results from the last years and actually to discuss some of the problems I decided to work on. And yeah, the reasons I like them. So this is the outline of the rest of the talk. So first, with a few slides, some general words about enumerative and algebraic combinatorics, which is my primary field of interest. Since I'm speaking at our seminar, I might go over this more quickly. And then I will share about 3 specific applications of enumerative and algebraic combinatorics over problems motivated by computer science. And then as part 3, I will try to tell you about another main theme in my research, which is explaining some surprising observations on combinatorial objects. So as I mentioned, one criteria for me to like a problem is that, or a conjecture is that it is very surprising. So I will share 2 such surprising results. Finally, if time permits, I will try to tell you about some exciting applications of machine learning to combinatorial conjectures. Okay, so when people ask me what kind of math do I do, I like to tell them this sentence about enumerative combinatorics in particular. So it is, roughly speaking, about counting things that are difficult to count. But yeah, I also add that hopefully some of these things are important, right? And yeah, so we have enumerative combinatorics, which looks at counting questions, and algebraic combinatorics, which tries to use some algebraic techniques to attack these questions. And a few years ago, a very important article was released by Richard Stanley, which discusses the history of the subject. And yeah, indeed, prior to 1960s, enumerative and algebraic combinatorics was more or less considered to be a set of ad hoc problems and unrelated between each other. And Giancarlo Rota had a major contribution to change this and to establish tight connections between these problems and certain algebraic techniques. And yeah, these are a few topics substantially developed by Rota there in algebraic combinatorics. And okay, later on, of course, other people had contributions like his student Stanley and Adriano Garcia, that will have a special seminar later this semester, Dr. Z, of course, and then, yes, several other people. And okay, nowadays, enumerative and algebraic combinatorics has gained some traction because of its applications to theoretical computer science, and this is admitted even on the website of the Institute of Advanced Study, which is considered to put more emphasis on more fancy sounding topics in general, but yeah, they also like they admitted that yeah, enumerative and algebraic combinatorics has applications in the recent years. Okay, so let me now tell you about this first result I want to share. It's about application to sorting of an enumerative problem. And so to tell you about it, we'll need the notion of avoidance in permutations, pattern avoidance in permutations. So if we have a permutation, probably most of you know that we say that permutation pi contains certain permutation p as a pattern if there is a subsequence of symbols and that permutation pi in the same relative order as the elements of P. So here are two examples. So this permutation, for instance, contains the pattern 2, 3, 1 because of this subsequence in red, right? So 3, 5, 1, the subsequence has its numbers in the same relative order as 2, 3, 1. So 5 is at the place of the largest element, 3 is at the place of the second largest, and yeah, 1 is the smallest. Okay, so yeah, otherwise we say that pi avoids P, and yeah, we write this in this way. So for instance, here we don't have this pattern 1, 2, 3. Okay, and so this first application is connected to sorting with data structures. So Donald Knuth was the first to ask, okay, if I just give you these very basic data structures, stack, queue, and deck, then which permutations can you sort just using these simple devices? So you're not allowed to use anything else. And here is an example how can we sort a permutation with a stack. So if I take this permutation 5, 2, 1, 4, 3, then okay, what I'm allowed is just to push and pop elements, right? So I can push 5, then push 2, push the third element 1, and then I can pop 1 and 2 just to put them in front of the output. Okay, now my goal is to get 3, 4, 5 in the output. So I'm going to push 4 and 3 and then pop everything, right? Okay, so this is how I sorted this permutation just using a stack. And okay, his question again was which permutations can be sorted using just this device. And famously, he showed that the only permutations that you can sort are those avoiding this pattern 231. Okay, for the device deck, which is similar, but you can push and pop from both sides, not just from one of the sides. That's a result by Pratt a few years afterwards. And basically he found that now for deck, you have to avoid certain infinite set of patterns. Okay, good. So for the stack and for the deck, we know the answer, but how about sorting by a queue? Well, if I just have a queue, I can push from one side and pop from the other side. I cannot sort anything pretty much, only the identity, which is already sorted. Right? So because of that, when I was a grad student, I decided to ask this continuation of this question. Technically, okay, what if we consider special types of queues where we can, in addition, do cuts? So what is a cut? I can show you with this example. So now having certain part of the input in my device, in my queue, I'm allowed to cut this at a specific place and then exchange the parts. So it's like a deck of cards. It's like a cut of deck of cards. Like I can do this. Okay. So if I cut between 2 and 1 here, I will just switch them. And yeah, I will move this to the output. Then 3, I just push and pop. And now for the remaining part, I can cut after 6, and then I will get 4, 5, 6. Okay, so this is how I sorted this permutation using cuts. Okay, now I investigated this type of sorting thoroughly in one project in the past, and here are 2 results about it. So of course, we shall ask, a reasonable question to ask is which permutations are sortable with this type of queue, and the answer turns out to be only those who avoid these 3 patterns. Okay, which was sort of interesting. That was kind of an analog of the result of Knut.
Is there a nice formula? Is it on OAS, the sequence?
Yes, it is in the OAS. There is a recurrence relation. Yeah.
Thank you.
Right. And then the next question that one could logically ask is, okay, I cannot sort all permutations using these queues, but what if I can try to use the same queues several times in a row? Like, what is the minimum number of times I should use such a queue to sort a permutation pi? So if I denote this by cost, the cost of permutation pi, then that's another result that the cost of a permutation is always roughly n over 2 or below. Right? That's another sort of interesting result here. And in this project, I formulated an interesting conjecture that I got experimentally. It's related to the so-called in shuffles and Mons shuffles. So in general, the project was about trying to sort using shuffling methods. So, you know, these cuts are the simplest shuffling method that one can use. And there is literature about shuffling methods separately. And these in shuffles and Mons shuffles are 2 popular methods to shuffle cards. And okay, I basically asked if I use these to try to sort arrays, then it turns out, or okay, it's a conjecture, it's only partially proven in my paper, but it turns out with these two very famous, with these two shuffling methods, you can sort the same number of permutations if you use similar type of queue where you have to unload the entire content of the queue with every pop operation. Okay, so that was about the first result I wanted to share. The second one is about an application to searching. And some of you are familiar with this project, but I like it quite a lot. So that's the general goal of the project. If I have a plain tree and I try to do a search in it for some target, then how can I do this efficiently? That's again a very general question. And yeah, I focus specifically on the set of plain trees with fixed number of edges. So here, for example, are all these trees having 3 edges. There, of course, we have 5 of these. 5 is a Catalan number, so that's one of the interpretations of the Catalan numbers. Okay, and what is our problem here? So we're at the root of some of these trees with n edges. There is a target node that we want to find, and the question is how to search for this target node. And of course, when it comes to searching in graphs or trees, the two very popular methods that we teach in every undergrad class in algorithms are breadth first search and depth first search. And here is, for example, how we will traverse this tree with breadth first search. So these labels next to each node are just, we call them the BFS scores. Basically, okay, I will first visit node with label 0, then the node with label 1, and so forth. Okay, so that's breadth first search. For depth first search, another classical algorithm, we will we'll proceed in depth. So we'll first traverse the tree until we can in one direction, and then we will backtrack. Okay, and again, these labels, we call them DFS scores. All right, so now here is an easy question. If my target node that I want to find is chosen uniformly at random among all nodes in these trees, right, then which of the two algorithms is faster in expectation? And okay, the answer is that they will have the same expected BFS scores and DFS scores. And okay, these expectations are important for us because they measure the average time complexity of the algorithm, right? So, and okay, these expectations are the same, of course, because we have the same chance to pick each of the labels 1 to n, right? So, and that's why this question is not very interesting. So we don't have anything to compare. These algorithms will perform in the same way. Okay, but here is a more interesting question. What if, again, we try to compare the two algorithms, but the target X is at some fixed level L, right? So for example, here, if we again look at those trees with 3 edges and the fixed level is 2, we have these 5 possible targets that are circled. Okay, and then, okay, if my target is picked at random among these 5 nodes, then which of the 2 algorithms, BFS or DFS, will be faster in expectation? That's my question. And what I like about this question is that at the very beginning, we have a clear intuition what should happen, but namely that for small levels, the breadth first search algorithm should be faster. For large levels, maybe DFS should be faster, but we cannot quite say where exactly is the threshold, and is it unique as well? Okay, so to resolve this question, we first use this fact, this theorem, Dershowitz and Sachs, which basically gives us the total number of nodes on level L in these trees. Okay, so that therefore, since we want to compare the expected BFS and DFS scores, we just need to compute these big sums, total B and total D. And then once we have these, we can just divide by this number and that theorem to get the expectations. Okay, so we just need to find these total B and total D. Okay, so here is the first result related to this. That's a result with 2 other people. So for this total D sum, it turns out we have a very nice simple expression, namely L times this binomial coefficient. And to establish that, we use certain well-known bijection and a few other facts like the cycle lemma. So basically, using these tools, we managed to show that it suffices just to establish this identity. And we proved that identity combinatorially, showing that both sides count certain lattice paths. Okay, so yeah, this is the actual bijection that we used. That's a very classical one. So if you traverse a tree with DFS, when you go away from the root, you put an up step in a dig path. Otherwise, you put a down step. So, and this will be the specific bijection for this tree. And okay, the way we use this bijection is to show that, okay, those nodes at level L in the tree correspond to nodes at level L in the dig path. But for dig paths, we have some nice theorems like the cycle lemma to count, to compute several sums and quantities. And basically this total this sum, we managed to show it's this left-hand side, basically. Almost, okay, divided by L. Okay, so we found this total D, and by that the expected time complexity for the DFS. For BFS, the situation was a bit more complicated. So we first try with generating functions, and I will skip some details here, but we define certain generating functions, and we found that they're related to these very simple Fibonacci polynomials. And the Catalan generating functions, specifically, we found these equations for these generating functions, and this helped us to find this not very nicely looking expression for this total B. But again, our goal was to compare this total B with what we found for total D, right? For the DFS, and we couldn't do that. Basically, we had partial progress. So we needed another formula for this total B. And here we utilized some other results of Hungarian mathematician Takács. And this helped us to get this new expression for total B. Now, with this new one, we managed to also use some asymptotic bounds for this binomial coefficient and for this sum, the so-called Berry-Essen bounds, the central limit theorem, to get actually the asymptotics of this total B. And okay, this is what we got for the asymptotics here. And all of that helped us to get our main result related to this project, which was that basically if the level L is below a constant times root n, then BFS is the better choice in expectation. Otherwise, DFS should be preferred. Okay, we also generalized what we found for the average time complexity of BFS, but for an arbitrary Galton-Watson tree, not just for plain trees. And okay, another interesting thing here is that we first suspected that the threshold that we will find will be probably the average level of a node in our family of trees. So we had this theorem of Flageolet and Sedgwick, which is saying that the average level for these nodes is roughly 1/2 square root of pi n. So there is a small discrepancy. So remember, we found that our unique threshold occurred at this constant 0.789 times root n. But 1/2 square root of pi is roughly 0.886. So yeah, there is a small discrepancy, and it would be interesting to explain it. Okay, and the third promise application of enumerative combinatorics to algorithms is here on this slide and the next few. It's about application to random sampling, another important question. So this is the question how to generate trees at random and in general Catalan objects. Here you see two pictures, one of all binary trees with 3 nodes that are trees having either 0, 1, or 2 children. And on the right, you see all the full binary trees with 4 leaves. These are trees where every node has either 0 or 2 children. And I purposefully draw them like that because just this picture illustrates a very simple bijection between the two sets. So if you take, for example, the first one and you add some edges so that every node here on the left has 2 children, then you get this first picture on the right. And the same for the others. So this illustrates one bijection between the two sets. And luckily, we have several such bijections between classes of trees counted by the Catalan numbers. So because of that, if we just find a way to generate a random say, full binary tree with n+1 leaves, then using these bijections, we would be able to generate random objects in the other classes. Okay, so that's quite nice. And this project, this problem itself was graciously shared by Dr. Z with me. So the idea was to find such a generalization of the famous algorithm of Remy, which was an algorithm to generate such a full binary tree. And it relies on this recursive form of this identity for the Catalan numbers. So we have this formula for the Catalan numbers. Equivalently, we can write it in that recursive form. And using that recursive form, this French mathematician Remy devised a really beautiful and simple algorithm to get a random such full binary tree. It's described here with these 3 steps, but it would be easier to look at an example. So basically, if I already have certain tree, it's enough to pick a random node of that tree and then pick a direction, either left or right, and then move the entire tree in that direction. In the other direction, just add 1 more leaf. So for instance, here on the last step, the random node that has been picked is the root. So we moved the entire tree to the right, the direction that has been picked. And in the other direction, we just added 1 leaf. Okay, so that's the entire algorithm, 3 simple steps. Very nice. And yeah, the idea of Dr. Z was to generalize this to forests. So here a forest is, we can think of a forest as a list of such full binary trees. However, they must have n leaves in total. So we look at the total number of leaves in them. And okay, these objects are counted by the so-called generalized Catalan numbers given by this formula. And we have the similar recursive form for this formula. And yeah, in this project, we proved that in the same spirit, the same beautiful bijection was generalized, in fact. So yeah, we gave interpretations of these terms here on the left and on the right. And okay, this as a result gave a linear time and space algorithm for random sampling of these forests. Okay, so I have prepared to talk about 2 more results, about 2 surprising observations that we explained with students. But yeah, I guess I don't have time for that. I will skip this part. One of them is about a nice chess tableau fact. Yeah, I will unfortunately skip that. The other one is another bijection which explains why 2 sets seemingly unrelated, like the 4-3-2-1 avoiding involutions and the so-called core partitions, namely these n+1, n+2 core partitions. These 2 sets turned out to be equinumerous, and we found an explanation illustrated with this example. And this is with the Rutgers student in my number theory class. So I will use the last few minutes to say a few words about the future directions. So yeah, I will try to work on more problems with applications to theoretical computer science and other areas. Also, this other main theme of my research about surprising conjectures and observations and combinatorial objects, something I like too. But recently I heard about a nice, really exciting idea related to the so-called reinforcement learning method. And with this idea, actually people attack combinatorial conjectures nowadays. So this reinforcement learning is a specific type of machine learning where basically we are in an unknown environment and we try to figure this environment out. We try some decisions, we get some feedback, and based on that, we try to figure out what are some best actions we can take in every state. That's very high level description, but this reinforcement learning turned out to be very useful and successful in games. So I here prepared a few slides related to the history of games and humans versus computers in games. Famously, Garry Kasparov lost from a computer in the 90s. And later on, 2016, Google DeepMind developed a software that beat one of the strongest Go players. And out of this success came out this AlphaGo Zero, and later on this other software, which is even more general, called AlphaZero. That was a paper published in Nature. So this AlphaZero basically achieved superhuman performance in multiple games, like the same software, the same program. Just after a few hours of training, it achieved really remarkable performance. And okay, of course, this AlphaZero uses deep reinforcement learning, which is reinforcement learning with deep learning, a combination of these. And Adam Wagner, who talked on our seminar last year, had a very exciting idea to disprove conjectures in combinatorics using RL. So this in bold is his idea. So define the construction. If you have a conjecture in combinatorics, you usually need to construct some extremal object, right? And basically define the construction of this object as a game, and then use reinforcement learning to train an agent to play this game. Okay, and he disproved a few conjectures using this idea. Here is one of these conjectures. I added this slide to illustrate how he defined this as a game, but I will again skip that part. And just on my last slide, I will say what I will try to do here. Basically, I want to combine his idea with this very novel new architecture called CAN, which stands for Kolmogorov-Arnold networks. That's there was a paper a few months ago about how this architecture turns out to be very efficient. It's an alternative to the standard multi-layer perceptron architecture, and yeah, it's faster to train and it has better interpretability. So I have a list of conjectures I want to attack with this new approach, this RL idea and this new architecture. So yeah, I will stop here, it turns out.
Well, thank you, Stoyan, for a very illuminating talk. Any questions? I have a quick question. First, you talk a lot about sophisticated results comparing expectations. Do you know anything about the variance and more information about the distribution, more higher moments?
Yeah, I guess you're talking about
The depth first search versus
yeah. No, basically, yeah, that's an interesting question. There is this average case analysis of algorithms, right? But no one talks about the variances in these cases. Yeah, maybe because the variance doesn't evaluate the complexity of the algorithm itself, right?
And another question: this binomial identities are the famous one like Van der Mond, or
which identities?
In one of your slides you had a very hairy combinatorial binomial coefficient identity. So
This one.
It is like one of the standard ones, like Van der Mond or Salzos?
No, so we use this cycle lemma, which of Motzkin and Dvoretsky,
Can
right?
you use WZ also for this one? It looks like you may.
I think you can, yeah. But yeah, we got combinatorial proof. So.
Yeah, anyway, beautiful results, the total.
Yeah.
Other questions to Stoyan? In this case, I have one more question. Machine learning is a ready-made software, so you can plug it in, or you have to make it yourself from scratch to implement it using machine learning?
Yeah, so you remember Adam, right? He talked at our seminar. He has some code online, but he now moved from academia. He's now at Google DeepMind. So I think he works on something else now. Maybe he's not very active with this idea, but I like it a lot, and I think several other people work on it, and it's very promising.
So you have to implement it. Use Python?
Yeah, actually, interestingly, one student of Vince Vater and Vince himself also got interested in this.
Nice.
And we're in contact, so we
That's
work
very
on
promising. Keep it up. That's nice.
Yeah, this semester I will work on this.
That's good. Okay, any questions? Well, thanks so much for a very fascinating talk. And please send me the slides and let me know when the recording is available. Thank you, everybody, for coming. See you next Thursday. Bye-bye. Thank you.
Bye.
Thank you. Esther, please end this meeting. Thank you.